Okay, now we just drew this three-body diagram and analyzed it so we know what this tension is and what this normal force is. And so we've got everything that we know here. Now we're going to have to face this one. And so once again, let's draw our free body diagram. So we have the little block that looks like this. And then in this direction we have 866P. And in that direction we have 0.5P. And remember, those are the coordinates based on that force at the 30-degree angle. And then I have a downward acting force of 392.4 newtons. That's the weight of the block. And then I'm going to have the normal force in that direction. It'll be the normal force for block B, though. And friction always opposes motion. It's absolutely clear that if I've got an unbalanced force in that direction, the block wants to go that direction. So we're going to say that our friction force at B comes back in this direction, and it's equal to 0.25 NB, like that. Now, this problem is, oh wait, we forgot the tension. We calculated that the tension force was 98.1 newtons. So it's 98.1 newtons going back, and I think I have everything on the diagram now. The problem here is I've got P and I've got NB. That's two unknowns. That's a good thing because I've got two equations. But the way these are set out, both of these unknowns have components in the vertical and they also have components in the horizontal. So it's not quite as easy as the first three-body diagram. But what we can do is we can sum forces in the x direction. And it probably doesn't matter whether we sum forces in the x first or we sum forces in the y first, but either way we can sum these forces, and I get minus 98.1 in that direction plus 0.866 P minus 0.25 in B. So I got 98.1, 866 P minus 0.25 in B, and that's equal to 0. Now, if I play with that a little bit, I can say 0.25 NB is equal to 0.866 P minus 98.1. Now, ultimately in this problem, I'm really not trying to calculate NB. What I'm trying to calculate is P. Because if I go back over here to my problem statement, it says determine the maximum force P that can be applied to the system without initiating motion. So it might be kind of nice if I took this equation and expressed NB as a function of P in the other variables. Now, if I do that, 0.25 over 1 is 4, so I take the 0.866 times 4, and I get 0.866 times 0.866, times 4, and that turns out to be 3.464 P minus 98.1 times 4, which is 392.4. Okay, and that is not anything, that's just a little thing on the paper. So you know what? What a cool thing these things are. So it's 3.464 P minus 392.4. That is my equation when I sum forces in the x direction. Now, if I sum forces in the y direction, what I get is minus 392.4. That's this one. And then plus 0.5p, that's going up, plus NB, which is going up. So 0.5p is up, NB is up, 392.4 is down, so that's equal to 0. And then it's pretty simple for me to say that NB is equal to 392.4 minus 0.5p. Now, I have this expression which relates P to NB, and I have this expression which relates P to NB. Both of these are true because they're equilibrium equations, and so at that point, all I have to do is take this equation and set it equal to this equation. Okay, and to do that, I'm going to say 392.4 minus 0.5p is equal to 3.464p minus 392.4. Well, if I bring this one across, I'll have 392.4 times 2, which will be 784.8. And then if I take that one across, I'll have 3.964p. And so I take 784.8 and divide it by 3.964. And I can find out that my value of P is 198.0 newtons as shown. And of course, as shown, is 30 degrees above the horizontal. So that's my answer, 198 newtons. And it's just that simple.